Okay, this is the wrap-up mini lecture for Chapter 20. The good news is that there will be a lot of examples in here, so hopefully that will help cement some of the craziness in this chapter. And as usual, the craziness is encapsulated beautifully in the reactions of organometallics. You knew we would get there. So we've looked at all kinds of things in this chapter, looking at carboxylic acid derivatives, that is, carbonyls with a leaving group attached. And we've learned from the get-go that we can add heteroatoms like alcohols, water, etc. to make esters, and so on and so forth. We had this little weird break in the middle with the Gabriel and the haloform reaction, and then we started looking at our hard electrophiles, the H- that we just looked at in the previous mini lecture, the hydride reagents, and now R-. So, what do organolithiums, Grignards, cuprates do with these molecules? Well, they present, once again, the issue of selectivity. Okay, what you can see right here is that it would sure be nice, wouldn't it, to have some R- that very logically should do up, tetrahedral intermediate, down, and out to give us that ketone. That would make us happy. New carbon-carbon bond, great functional group that we can do a lot of fun things with, but turns out that we can't make it stop. In other words, when we add our organolithium or our Grignard, even if we specify one equivalent, let's say we're using methyl lithium, we're still going to get it to add twice and give us the tertiary alcohol wherein two of the alkyl groups on the tertiary alcohol are identical. And that is because as soon as the ketone forms, the ketone is more reactive than the ester, and so the subsequent addition, the second addition, takes place much more rapidly. So, no selectivity with Grignards or organolithiums. So, let's review selectivity. We learned in the hydrides area that sodium borohydride, since it's so mild, is actually a very selective reducing agent. It has to have a really strong electrophile, and it reduces it down to an alcohol. So sodium borohydride can happily react with aldehydes, ketones, and the most reactive carboxylic acid derivative, the acid chloride, to give us reduction. We also learned that dibol and the lithium tritert butoxide aluminum hydride, they're selective too. It's not because they're mild, it's a combination of features. The fact that there's only one hydrogen on there is part of it, but also because of sterics and the fact that we can control the solubility and reactivity and keep the temperature down. So these are selective because they manage to add once and only once and stop the reduction at the aldehyde. So we would really like to have something in the organometallic realm, I should say, that acts like this. Is there not some organometallic that would just add once selectively and then not add again to give us the tertiary alcohol? Well, there is, and that organometallic is the cuprate. Okay, so cuprates once again are special. They're selective R-, and luckily enough, a cuprate will add only one time to give the ketone. So, a recap of cuprates, remembering that we make our cuprates by taking an organolithium of any description and adding it to copper iodide to get the dialkyl cuprate. That's how we make our cuprates. So cuprates are special. They undergo three reactions that organolithiums and Grignards don't, and won't, and can't. Cuprates do conjugate addition. So for example, when I add diethyl cuprate to an alpha-beta unsaturated carbonyl, I get 1,4 addition, and ultimately after workup, addition of my nucleophile, my R- at that gamma carbon. Cuprates are special too because they do the coupling reaction that Grignards and organolithiums cannot and simply don't. And this is a really nice feature that even on an sp2 hybridized carbon, especially on an sp2 hybridized carbon, I do my tinker toy chemistry, I can simply put my ethyl group right where that bromine was and make a new carbon-carbon bond right there. Works wonderfully. And then now the example for this mini lecture is that if I have an acid chloride, which again we know is the most reactive carboxylic acid derivative, I can add a cuprate to that, and miraculously it will in fact do one and only one up, down, and out to give me the ketone, and it stops there and we are happy. However, we are not happy in that I continually add an extra carbon here. So it's really just the ethyl ketone, not the methyl ketone. So we'll just kind of erase that. Ha ha ha. There you go. That's the right product. Okay, because I just added that piece. Alright, so cuprates are special. Make sure you keep them in your synthetic toolbox and don't get them mixed up with the not so special, not so selective reagents like the elephant gun of hydride reagents. Lithium aluminum hydride, for example, reduces everything as far as it can, which is down to the alcohol. So the not so selective reagents for reduction are lithium aluminum hydride, reduces everything. What is it going to reduce here? Let's see. I have an amide here. I have an amide here. That looks like that's about as far as I can go. Those both get reduced to the amine. The CO double bond is GONE. And then the not so selective organometallics are the organolithiums and Grignards. Don't try to stop them at the ketone stage. It just won't work. Invariably you will get the tertiary alcohol again pointing out that when you have a tertiary alcohol with two alkyl groups that are identical, that's a dead giveaway that you're starting from an ester and adding a Grignard or an organolithium, but no ketone isolation. It just keeps going. Alright, so the rest of this mini lecture is examples. Alright, we have a chiral methyl ester. Wonder what that is. Looks like a... is that R or S? Good review for the final. We're going to have to do this again. The H is facing away from me. Highest priority is on the right. That looks to me like an R methyl, because here's my methyl for the ester. And then it's a 1, 2, 3, 4, 5. It's a pentanoate, but it's a 1, 2. So this is R methyl space 2-methyl pentanoate that I am reacting with the propyl Grignard, and that should give me that. And if I think mechanism, I'm going to think I have this, and then I'm going to say, but wait, it's not special. The ketone is more reactive than the ester, so my propyl group will react again to give me the addition of 2 propyl groups and the tertiary alcohol. How about this reaction? Now we've got the special organometallic, a cuprate. We just have to figure out where in the world it's going to react. Is it going to do conjugated addition? Is there a coupling reaction going on here? These are all just, these are ethers. There's an acetal. Ether. Ethers just don't do anything, and you know acetals are stable to base. So apparently my cuprate will be reacting with the acid chloride to put the methyl group, boom, right here. In other words, the cuprate is my friend, it's special, and it can do the up, down, out only once and stop at the ketone stage. Very helpful. Now, what if I want to take this further? A little review. Again, taking the big picture look at this thing, what we see is that we've got a couple changes here. We have gotten rid of our acetal, and we have changed our ketone to an alkene. So that's a good little problem there. We've got to do two things. In what order should we do this? It's clear that this would have to be Wittig chemistry, and this is just hydrolysis. But if we do hydrolysis first, then we have the problem of having two ketones that could undergo Wittig. So we must think about the order of addition in which we do this. We have to do the Wittig first to make the alkene, and then we can do the hydrolysis to deprotect that ketone and have our final product. Another example here, all right, a regular organolithium. I'm going to think carbanion, up, down, out. That should give me this. Well, it shouldn't give me that because I've already done the out part. Didn't see my down arrow there. Well, seems to me that would just go right back there and react with the ketone. So I've got an equilibrium going on here. But at the same time, I still have a reactive ketone and a much more reactive nucleophile than the O-. So I think that it's probably pretty reasonable for this guy to attack. And bottom line, it adds twice because I get that intermediate ketone, and then upon workup I get the diol shown. All right? And then finally, synthesis examples. I have an alcohol, the bells and whistles, ding ding ding, I have two ethyl groups. That is telling me that a real logical disconnection would be to go back to the ester. So I could, for example, add, excuse me, that is not what I want to write. I want to write ethyl magnesium bromide times 2 and then workup. That would get me this. But there's a million different ways to make alcohols. Why don't we just hydrate this alkene right here? It's regioselective. It would make perfect sense that the alcohol would go here. So why is that a bad idea? It's a bad idea because I have another alkene in my molecule. There's no way I'm going to be able to hydrate one alkene selectively when I have both alkenes in there. Granted, this would be the more reactive alkene because it's tri-substituted, but still, this is the much better disconnection. All right, how about a ketone? Well, now we know a different way to make a ketone. So there's lots of ways to make ketones. Good review here. We can oxidize an alcohol using chromium of some description. It could be PCC, it could be chromic acid, you name it. We could do a disconnection right here and alkylate this methyl ketone by using, say, 1 LDA minus 78 to get the kinetic enolate, and then add an ethyl electrophile like ethyl chloride or ethyl iodide. But now we've just added into our synthetic toolbox, yay. Well, actually, we don't want the ethyl one now here. Got to erase my disconnection. For this route, we're going to put a C3 piece on. So we would need the propyl cuprate. So yay! Now I have 3 different ways of making ketones, which really fills up my synthetic toolbox and gets me out of a bind if I'm stuck on a quiz or an exam. Alright, so that's a lot, so we need to wrap it up with a really wonderful joke. Wonderful joke. I make no promises. So it's all about a florist. It's a florist run by friars. So these poor friars were behind on making their payments for their belfry. So they opened up this florist shop to raise some money. Well, everybody liked going to this florist shop because, you know, they were supporting the men of God. But the rival florist across the street thought that was really unfair competition. So he politely asked the good fathers to close down. But they said, no. He kept losing money, and so he went back and he begged the friars to close their florist shop. And they kind of just completely ignored him. So that put the rival florist in kind of a dire strait. So he hired Hugh McTaggart, who was this big old thug, really rough, vicious thug in town. And Hugh, quote unquote, persuaded them to close by beating them up, trashing their store, and saying he'd be back if they didn't close up shop. So, needless to say, they closed up shop. And that proves, of course, that Hugh, and only Hugh, can prevent florist friars. Okay, that's all right. We're out of here.